Hello students, welcome to experiencetutor.com. Today we'll go through class 11th mathematics complex number part 4.
Let us start with the welcome message. Dear students, welcome to our channel experiencetutor.com. In this channel, we will teach physics, chemistry, mathematics and biology for the students of class 10th, 11th and 12th and those who are appearing for the school board examinations and entrance examinations like IIT, NEET and all state level engineering and medical examinations. This course is organized according to different topics for each subjects. Therefore, it contains separate video for each and individual topics. Hence, it covers complete syllabus for CBSE, ICSE, ISC and all the state board examinations and engineering and medical examinations. You can also find the relevant topics for foreign school examinations like SAT, IGCSE, IB, etc. Enjoy your learning. Thank you.
Let us start with our first question for today. Express the following in the form of a plus ib. First part is 4 plus 3i upon 5 plus 4i. Let us solve this one. So we have written 4 plus 3i upon 5 plus 4i. Then we'll write it as is equal to 4 plus 3i into 1 upon 5 plus 4i. After writing it, we can multiply the same with multiply and divide by 5 minus 4i five minus 4i closing the bracket with 5 minus 4i on denominator. So we can get it as 4 plus 3i multiplied by 5 minus 4i divided by 5 square minus 4i square, which can further be written as 1 by 41 4 plus 3i bracket 5 minus 4i, which can be solved as 1 by 41 20 plus 12 plus I minus 16 plus 15. After that we can write the same equation as 1 by 41 bracket 32 plus I minus 1, which can be written as 32 upon 41 plus I minus 1 by 41. Now let us solve the next sum. One minus I whole square upon 2 plus I, which we can write as 1 minus I whole square into 1 upon 2 plus I. And next step we can write the same as 1 minus I whole square, this is here, whole square into 1 upon 2 plus I into 2 minus I upon 2 minus I is equal to 1 plus I square minus 2 2 minus I upon 2 square minus I square is equal to here we have missed I, so is equal to 1 minus, instead of I square we can write minus 1, so 2I 2 minus I upon 4 minus, instead of I square again we can write minus 1, which will be plus 1, and here we can write minus 2I into 2 minus I upon 5. If we multiply this, then we can get as minus 4I plus 2I square upon 5. Now again we can write the same as a minus 4I, instead of I square minus 1 if we put, then this will be minus 2 upon 5. The same can be written as minus 4I upon 5 minus 2 upon 5. Therefore we can write the above as plus I minus 4 by 5. So we have represented in A plus IB form. Now our question is, prove that the complex number 3 plus 2I upon 2 minus 3I plus 3 minus 2I upon 2 plus 3I is purely real. So I'll write this as so we can write the same equation as 3 plus 2I upon 2 minus 3I multiply by 2 plus 3I in the numerator and denominator. Similarly, we'll do the same thing with this equation. 3 minus 2i upon 2 plus 3i multiplied by 2 plus 2 minus 3i in the denominator, in the numerator and denominator. Upon solving, we can get 6 minus 6 plus I 9 plus 4. This is simple multiplication. You can do it in any way. So this will be 2 square minus 3i square, a square minus b square, plus this can be written as 6 minus 6 plus I minus 9 minus 4. 4 minus 9i square. Same way we have solved it. Now we can write the same as we'll solve this above equation and we'll simplify it, and on simplifying we can write it as 13i will be left in the numerator, and it will be 9i square here. It will be 13 will be left here, plus again I can put it as a bracket here, and here same way minus 13i will be left upon 13. So here 0 is the answer. So which can be written as 0 plus I 0, so we can write it which is purely real. Which is purely real. Conjugate of a complex number. So what is conjugate of a complex number? The reflection of complex number uh, z is equal to x plus iy in the real axis mirror is called conjugate of z. This point can be denoted by z conjugate is equal to x minus I y. Let us see how we can represent it. Say this is the mirror and a point, this this is the jet, so here is z and z is equal to x plus I y. The conjugate can be represented by this, where conjugate can be written as x because it is positive x-axis, but it is negative y-axis, so it will be minus iy. Hopefully now it is clear what is conjugate. And properties of conjugate of a complex number. So let us see the properties of conjugates. Properties of conjugate of a complex number. So first property, conjugate of a conjugate complex number is the complex number itself. Second property, modulus of conjugate is equal to modulus of a complex number is equal to modulus of its conjugate. We can write this also, minus complex number, or which is equal to minus of conjugate of z, same thing, or it can also be written as modulus of I z. Similarly, it can be written as modulus of I z conjugate. Rule number 3. Z and conjugate of z is equal to Z square modulus of Z square is equal to real Z, real part of the complex number whole square plus imaginary part of the whole complex number whole square. Rule number 4 is real part of Z, real part of a complex number is equal to the mean of the complex number and its conjugate, and imaginary part of the complex number is equal to Z minus Z conjugate upon 2i. If Z is purely real number, then imaginary Z is equal to 0. So we can write if Z is or Z is the element of real number, is a real number, then imaginary part of Z is equal to 0, which implies that Z is equal to modulus conjugate of Z. Again, if Z is purely imaginary, then real Z, real Z is equal to 0, which implies that Z plus conjugate of Z is equal to 0, or Z is equal to minus conjugate of Z. Rule number 5. Rule number 5, we can write Z1 plus Z2 mod is equal to Z1 mod or conjugate of Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2. In general, we can write conjugate of Z1 plus Z2 plus Z3 dot 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 Zn is equal to conjugate of Z1 plus Z2 plus Z3 dot dot dot. So this can continue till Zn. Here also this can be continued. This can be continued till Zn. So rule number 6 is modulus of Z1 or conjugate of Z1 multiplied by Z2 is equal to Z1 into Z2 or in general we can write Z1, Z2, Z3, Zn conjugate of this will be equal to Z1, Z2, Z3 conjugate, and this will go up to Zn. This can also be written as Z to the power n conjugate is equal to Z conjugate to the power n. Rule number 7 is if Z2 is not equal to 0, is not equal to 0, then Z1 upon Z2 conjugate is equal to Z1 conjugate upon Z2 conjugate. Rule number 8 is argument of Z plus argument of z dash is equal to z conjugate is equal to 2k pi. K is a complex number. So these are the 8 rules for conjugates. Now we have a question. If z1 is equal to conjugate of z1 and z2 is equal to minus conjugate of z2 and z1 and z2 both are non-complex numbers, then find the sum of all the possible principal values of argument of z1 and argument of z2. So we can write it as if z1 is equal to modulus of z1 or a conjugate of z1, then which is given in the question, then z1 is purely real number. Z1 is purely real number, and in this case and in this case argument of z of z1 is equal to 0 or pi. Similarly, if z2 is equal to minus conjugate of z2, then z2 is purely imaginary. 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 And in this case, in this case, in this case, argument of z1 is equal to 0. In this case, argument of z2 is equal to argument of z2 will be equal to pi by 2 or minus pi by 2. Hence the sum will be equal to 0 plus pi plus pi by 2 minus pi by 2, which is equal to pi. We have a question: if z1 is equal to 3 plus 2i and z2 is equal to 2 minus I, then verify first z1 plus z2 conjugate is equal to z1 conjugate plus z2 conjugate. Second, z1 minus z2 conjugate is equal to z1 conjugate minus z2 conjugate. z1 multiplied by z2's conjugate is equal to z1's conjugate multiplied by z2's conjugate. z1 upon z2's conjugate is equal to z1 conjugate upon z2's conjugate. Now we'll prove it one by one. So first sum is uh, z z1 plus z2. We need to find it out. So z1 plus z2 will be equal to z1's value is 3 plus 2i and plus sign. Z2's value is 2 minus I. On solving this, we'll get, we can solve it here. 5 plus I. So conjugate of z1 and z plus z2 will be then conjugate of 5 plus I, which is equal to 5 minus I. Now right hand side we can write it as z conjugate z1 conjugate z2 conjugate sum. Now we can write 3 value of z1 3 plus 2i conjugate plus 2 minus I conjugate, which will be equal to 3 minus 2i plus 2 plus I, which is equal to 5 minus I. Therefore, we can write it as z1 plus z2's conjugate is equal to z1 conjugate plus z2's conjugate. Now we'll try to prove the second one, where the left hand side z1 minus z2's value will be 3 plus 2i minus 2 minus I, which is equal to 3 minus 2 plus I common 2 plus 1. So 1 plus, so here it will be 5 plus I. No, it will be 1, 3 minus 2, that is 1, plus here it will be, mm, here it will be 1 I. So 2 plus 1, so 1 plus 3I. So now the conjugate of z minus z1 minus z2 will be conjugate of 1 plus 3I, which is equal to 1 minus 3I. Now we'll see the right hand side, conjugate of z1 minus conjugate of z2. Just we'll put the values, 3 plus 2I conjugate minus 2 minus I conjugate, 3 minus 2I minus bracket 2 plus I, which is equal to 3 minus 1 and 3 minus 2, 3 minus 2 and I common, 2 minus 2 and minus 1. So which is equal to 1 minus 3I, which is, therefore we can write, therefore in this case also you can write z1 minus z2's conjugate is equal to z1 conjugate minus z2's conjugate. Now we can prove the third sum, where it says z1 multiplied by z2. First we need to find out this. So putting the value of z1 and z2, we'll get 3 plus 2I bracket 2 minus I. So on solving, we'll get 6 plus 2 plus I, 4 minus 3, which is equal to 8 plus I. Therefore conjugate of z1 multiplied by z2 is equal to conjugate of this is equal to 8 minus I. On the right hand side we can write the same as conjugate of z1 into conjugate of z2 is equal to 3 minus 2i or 3 plus 2i conjugate multiplied by 2 minus I conjugates. If we multiply, if we solve it, then we can have 3 minus 2i multiplied by 2 plus I, which will give us 6 plus 2 bracket plus I 3 minus 4, which is equal to 8 plus I. So if we find out the conjugate of this 8 plus I, it is 8 minus I. It is 8 minus I. Now if we find the conjugate of we have to prove it has been proved that so the values are same in LHS and RHS, this one and this one, so it is proved. Now the fourth sum is z1 upon z2. First we have to find out, then z1 upon z2 will be 3 plus 2i upon 2 minus I, which is equal to 3 plus 2i in bracket we can write 2 minus I, and we can multiply and divide by 2 plus I and 2 minus I, 2 plus I in numerator and denominator. Therefore we got 3 plus 2i bracket 2 plus I upon 2 square minus I square. So upon solving this, we'll get 6 minus 2 plus I 3 plus 4 upon 4 I square is equal to minus 1, which is equal to 1. So upon solving we can get 4 plus 7i upon 5. Therefore 4 upon 5 plus I 7 upon 5. Therefore, if we put the modulus of now if we put the modulus of z1, this is the value of z1 upon z2, so the conjugate of z1 upon z2 is conjugate of 4 upon 5 plus I 7 upon 5's conjugate, whose conjugate will be 4 upon 5 minus I 7 upon 5. Now in RHS we have to find the conjugate separately. So conjugate of Z1 is 3 minus 2i and conjugate of Z2 is 2 plus I. So we can write it 3 minus 2i multiplied by 1 upon 2 plus I multiplied by 2 minus I upon 2 minus I. So it will be 6 minus 2 plus I minus 3 minus 4 upon 4 square, 2 square, that is 4 minus I square, which is equal to 4 plus 4 minus 7I upon 5, which can be written as 4 upon 5 minus I 7 upon 5. Therefore, which is proved. Therefore, uh, z1 upon z2's conjugate is equal to z1's conjugate upon z2's conjugate.
And this is the end of this topic. If you like this video, please subscribe our channel and give us a like sign. Please click on the bell icon so that you get automatic notification when a new video is uploaded by us. Thank you for watching our channel.